quantum AI lab, which I initially joined as a PhD intern. And after graduating, I joined them as a scientist. To this day, I'm still like a visiting scientist officially for NASA and for an organization called the University Space Research Association. But starting this semester, I joined Purdue as an assistant professor in the chemical engineering department. And I'm very excited to be here for many, many reasons. Among them, the fact that here at Purdue, there is a lot of support to quantum computing research through the Purdue Quantum Science and Engineering Institute.
Yeah, this is Matthias Florian speaking.
Quantum
So
technology.
I just
and
placed
certainly like the
recently,
collaboratory,
and
the
you
Midwest
tried to
Quantum
call me back,
Collaboratory.
and I just
So I'm very happy to be here. Now, let me talk to you about something that we decided to call Sequoia. So it stands for Systems Engineering via Classical and Quantum Optimization for Industrial Applications. This is the name of my research group. And well, for those of you that don't know, the sequoias are like these big trees that grow in the west coast of the United States. They're amazing. They're massive.
So
they're impressive.
And
we also
order?
planted one here, so I have a mini sequoia in my office.
Plate, and I just chose one
this is
side.
not only me, but my research group, which is growing at a very, very fast rate, which is something extremely exciting for me. So right now we have some of our members, as you can see from the description there, they are working on more classical topics, process intensification, process superstructure design, because again, we're sitting in a chemical engineering department, but as you might see, my two,
add,
let's say newest PhD students, among them Icing, that is in the audience right now, we are going to be working on quantum-related research. In fact, Icing is going to be working in quantum.
I haven't. A
topic that we're super excited about. Anurag is going to be working on benchmarking quantum algorithms in chemistry and optimization. And Pedro down there is a visitor, hopefully future PhD student. I'm going to be showing some of the work that I have been doing with him. And there you can see our latest Christmas dinner party where friends joined us and suddenly we were 12 people sitting on the table. Okay, cool. So one question that you might ask is, what does this have to do with chemical engineering? How is it related to chemical engineering? And you're not the only ones that are asking such questions. In fact, the American Institute of Chemical Engineering reached out to me because they were like, okay, apparently this guy knows a thing or two about quantum computing. He's also a chemical engineer. How about if you write a perspectives article, like showing what we can do? And back then I was still, well, in fact, I'm still affiliated with Carnegie Mellon as an adjunct professor there in operations management and quantum computing, which might sound weird, but it isn't that much. And it will make sense towards the end of this talk. But together with some folks at Cornell and at ExxonMobil, we wrote this paper. It has gotten pretty good attention. And we identified like 3 areas where we believe that quantum computing might have a big impact for the field of chemical engineering, which is computational chemistry, optimization, and machine learning. They also happen to be areas that I'm deeply interested in. So there might be some bias in the first author of this paper. In any paper, there is some bias. So, and the conclusion is that although there is potential, there are so many challenges to overcome that if anything, it's encouraging because we're not going to be bored while working on these topics. So let me just jump right into it. And let's start with optimization. I'm going to set up the stage. And for everyone here to be in the same page, optimization is this exploration where we're looking for solutions that we call optimal solutions to problems in reality. And this is very obvious, very general and non-obvious process, and it can be time-consuming, expensive, prone to errors. So the way that we like to approach this problem is that we write a representation of the real world as a model, as a mathematical model, and then we sort of distill our understanding of the reality into that model. And usually we incorporate assumptions and simplifications because one thing is writing the model and another thing is actually solving. So we need to balance tractability and like fidelity of this model. So And useful part, and some that I have been working on, it's called mathematical programming, where we write this optimization problem in terms of mathematical equations. So functions that define an objective that can be either minimized or maximized subject to some constraints that usually encode the real physics or the real dynamics of the system that we are analyzing. And then we have something called variables, which are values that can change during this exploration. This might sound super basic for some people in the audience, might not be super basic for others. So I just want, again, to set up the stage. So when you start considering how to model the real world, you very quickly realize that the real world is abrupt, unexpected, discontinuous, non-smooth, and you need to incorporate that into the models if you want to solve these optimization problems. And here comes mix into your programming to the risk. And this is just a way that people have been using to approach this non-continuous reality. And it's basically enforcing that some of those variables need to take discrete values, need to take integer values. And you might think, okay, cool. What is this useful for? And in a nutshell, it's a universal tool for modeling. I mean, there are mathematical proofs that says that the moment that you start incorporating discreteness, you can start modeling like pretty much anything. Now, this condition, obviously it arises from like certain things in reality, they are discrete by nature, meaning like if I'm producing shoes, right, and I want to model the production of some shoes, an optimal solution cannot be 7.3, right? They need to be discrete numbers. But more importantly, they are used as triggers or switches for logical conditions. So we can start through 0, 1 variables, start encoding things such as disjunctions, implications. And this is where the actual power lies. Because, I mean, in decision processes, this is usually the kind of questions that you want to answer. So ubiquitous, omnipresent, call it however you want. But then there is this other observation, which is, okay, the word, besides being abrupt, is nonlinear, right? And coming from a field such as chemical engineering, where we encounter reaction kinetics, transport phenomena, all these things, they are very nonlinear, in fact. So I told you, you can model discontinuities with discreteness, but usually the physical rules that we want to incorporate into our model, they are naturally nonlinear. So this assumption that you can just take objective and constraints and write them as a linear combination of the variables, which is very common in some fields, for example, operations research, it doesn't hold in general. Like we cannot afford doing this. So suddenly our optimization problem, the functions that we include in the objective and the constraints, they can be nonlinear. They can be arbitrarily nonlinear. And well, I mean, this results in something that we call discrete nonlinear optimization problems. The people from operations research have given them a longer name, which is mixed integer nonlinear programs, but they basically encode these variables that can be continuous and discrete, constraints that can be linear or nonlinear, and it is computationally hard. Like if we get into the whole discussion of hardness of optimization, they belong to the NP-hard family of problems. So anyway, you might ask yourself, if you have never encountered this, you might ask yourself, okay, how hard can, like what is this whole NP-hard complexity telling us? And well, there is a finite number of combinations if we consider that the sets that include these discrete variables is bounded. There is a finite number of combinations. So somebody might suggest, look, take all the combinations, evaluate them, evaluate the constraints. It should be easy to evaluate the constraints. So you filter those that are infeasible, then you rank them according to the objective, and you're done, right? And sure, you could do it. The issue is that it would take a finite yet impractical amount of time to do this. And usually like this has to do with the combinatorial explosion of the number of solutions that there are. So I usually use this plot here to sort of visualize and give this message very clear, which on the x-axis has the size of some optimization problems, On the y-axis is just some counting. And I'm plotting the number of different solutions that might arise from the most basic combinatorial problem, which grows as 2 to the power of n, in the case that you only have binary variables, to more, let's say, practical problems that they have something called like permutation. For example, in the traveling salesman problem, where you're selecting like the route that you want to visit, that grows as something called the permutation, and permutations grow even faster. And I have like those dashed lines are just really big numbers. So basically, actually, let's see if I can use my pointer. Laser pointer. There you go. So, and there you can see that suddenly I have like these really big numbers, which is like, I don't know, the number of nanoseconds in a year, the number of nanoseconds in the age of the universe, the number of atoms in the universe. And you realize that for very modest problem sizes, you basically run out of practical time in order to solve this problem. So enumeration is completely like dismissed. Now, you might ask yourselves like, okay, these problems, they are really helpful for us to model things. Do we solve them in practice? And the answer is yes. Like these problems are being solved in practice all the time. If you think about the scheduling of pilots into aircrafts, these are huge, discrete, sometimes nonlinear problems that are solved on a regular basis. And you're like, okay, certainly not by enumerating them. How are they being solved? And the quid here, and if anything, the message that I want to transmit in this seminar is that we can design algorithms that people call them decomposition algorithms that basically break down the problem on tinier pieces. And those pieces, we use specialized tools for each one of them. Then we put together this solution, and that gives us optimal solutions to these complicated large problems. So now the question is, how do you break down the problem? How do you solve the subproblems? And those are like questions that we encounter on a regular basis, we as algorithm designers for this kind of stuff. But they have been extremely successful in the classical world. And if anything, I feel that we have a lot to learn from those that have been working on this for years, and we can use some of the learnings that they have, like some of the things that they have learned throughout the years, for us to basically use novel hardware and so forth. Okay, anyway, so these are some contributions that me and my group have been doing in this space. And this one is particularly relevant because I started looking at the classical methods of solving these discrete nonlinear optimization problems. And we did some benchmarking. Because obviously stopping at the worst case complexity, doing just some analysis, it would just tell you, okay, this might take exponential time to solve, and you can come up with examples. But when you actually go out there and try the practical examples, I was just telling you, these are being solved on a regular basis. How fast? How efficient? This is a question that needs to be answered from a more experimental side of things, from a more, let's run the algorithms and verify how fast, how efficient are they whenever you try to solve practical problems. So we did that with the classical solvers. We got a lot of attention there. And this, in fact, was motivated us to start doing this with quantum methods. So basically, the Anurag's PhD thesis is doing this for quantum methods. So that's fun. That's exciting. We also we're working on how to modify those decomposition algorithms using, I don't know, things from algebraic geometry, advanced linear algebra algorithms, and so forth, in order to make them more efficient. Because although these algorithms have existed for some time, there is a lot to be done, and you can still push the limits in there. Like if anything, like that benchmark study told us, like there is a huge gap between what you can model and what you can solve practically. And we need to close that gap because we're always looking to solve larger problems, deal with more complicated problems, and so forth. And we can close that gap just by doing some investment in time and effort in designing the algorithms. finally, I like putting all this stuff into software. So initially we had some implementation for commercial solvers that were really performant, and they were like, nah, let's put them open sourced. So we have been developing codes for the algorithm implementation and for the benchmarking as open source options. So that's something that, I don't know, aligns with the way that I like working. And if anything, like I'm not a perfect coder. I'm a sort of lousy coder, in fact. So please go into the codes, and if you find errors, let me know. We'll fix them, right? So, and this is for the community itself. All right. Why? Again, this question comes often in my seminars, so I'm just proactive in answering it. Why does a chemical engineer care about this? And there are many, like this modeling framework is so general that it allows us to put many applications as discrete nonlinear optimization problems, among them many in chemical engineering. So here I just give 4 examples, one in distributed manufacturing, another one in catalytic distillation, maintenance optimization, refinery operation, and scheduling, that all fit this kind of description. And then the moment that you like start working on them, you realize, oh my God, these are really challenging yet interesting optimization problems, and we can apply many of the techniques that we have been using for that sense. Okay, anyway, this is a quantum talk, so I need to talk about quantum, right? And this is how I got started in this field. Basically, they at NASA, they had just purchased quantum annealer, which I hope for this audience is clear, but if not, like it's a machine that is designed to solve optimization problems, hopefully taking advantage of quantum mechanical phenomena. And they had this compiler issue. They needed to fit like arbitrary problems into their chip because it's not like fully connected and so forth. And then I realized that you could write this down as one of my discrete nonlinear optimization problems. So I was using classical optimization to solve a problem in quantum. And basically this, we got a paper there, and it's interesting and people are using it. Now, once I was there, I realized, wait, so there are quantum computers that are able to already tackle interesting optimization problems. So we can start asking and answering questions such as, how should you write down an optimization problem such that one of these quantum annealers or other quantum methods for optimization can solve it more efficiently? And you can use the same approach that I was using before on benchmarking the methods, just running the different, we call those formulations, just different ways of writing the optimization problem, and realizing which one works better. And then we can match that with some theory. And certainly, like, we needed to start somewhere. So we needed to start small, and we were doing like some stable set and mixed K-colorable subgraph. We realized very soon that certainly the size of the computers are far from the sizes that some of the optimization problems need to be solved. So there is an interesting track which is concerned with basically doing resource estimation. How big do these computers need to be in order for us to solve problems that are interesting for a given application? And that's exactly what we were doing with ExxonMobil. So they at Exxon, they have like this huge fleet of ships that transport liquefied natural gas across the world. And you need to basically, those ships, they stop at different ports, they get gas, they go to another port, they drop gas, blah, blah, blah. This is a tremendously large problem. And they're like, and they did care about this. So they're looking at different technologies to solve this. And then they asked, like, can quantum help? And we went there and we were like, okay, let us figure it out. I also used this slide deck because it sort of highlights one of the issues, the biggest issue, in my opinion, that currently quantum computing faces, besides, like, you know, the universe messing up with your computation, which is hype. So I guess you can read there, but this shows like a news article that they published at CDNet, which I heard that is like apparently a popular site online, which claims IBM and ExxonMobil are building quantum algorithms to solve this giant computing problem. And if you start reading through it, it's like, whoa, oh my God, these people are really solving like practical optimization problems. This is based on an article that IBM put based on our problem, which is ExxonMobil and IBM explore quantum algorithms to solve routing formulations. Once you dig deep enough, you'll find our paper and look at the huge problem that we're solving. This is the whole network of distribution that we're solving. You can solve this problem by hand. In fact, I have a couple of slides that solve it on PowerPoint. So certainly, like how this tiny problem got blown up into, whoa, they're solving like the whole the whole supply chain of liquefied natural gas. It happened within 2 weeks in front of my eyes, right? I was part of the story. And this is the hype that we need to control for quantum computing. It is terrible how damaging this can be for our own field. Because then suddenly, if somebody comes and tells me, David, how about if you apply that algorithm for, I don't know, other logistics problem, I tell them I cannot do that because I physically cannot do that and the computers cannot do that. And part of the answers that we're providing is how large does a computer need to be for us to be able to solve practical problems? And it's far, far, far from what was available back then and what is available today, in fact. They will be disappointed. They'll stop paying attention to us. And this can be very, very damaging for our field in general. So sorry for spending some time in this, but it needs to be said. Anyway, other stuff that you can always reach out to me if you want to talk, because they're like, I wouldn't call them side projects, but they're just like other projects that I'm working on. Now I'm working on how to compile on different kinds of computers. I work on distributed quantum algorithms for graph problems. So finding Steiner trees when you, instead of having a single quantum computer, you have a network of quantum computers and they start like sharing qubits among them and things get really, really fun. I work on this decomposition based on capacitive programming, which in fact I put some slides here so you will know a little bit more about this. And in general, I do care about benchmarking quantum computers. I do care about, like, I want to have cold numbers back up the claims that I'm making. And I like horse races, so let's just put them and make them compete against each other to see how good they are doing. And in fact, whenever they win the race, this is a slide I took from IonQ. They, in one of their internal presentations, they were using some of the graphs that we made, because obviously in that particular competition, they were beating Quantinuum and IBM and Rigetti. Certainly, like, you will not see these results in Rigetti's slides, right? Because, well, whatever, right? Somebody needs to do these comparisons. Anyway, about future research, and I use always like the apostrophe. Now I'm using the apostrophes under future. Again, part of this talk is sort of recycled, and I was using this slide in particular when I was applying for faculty jobs 3-4 years ago, and I was planning to do this, and I just used the apostrophes because this is currently what we're doing. We're designing algorithms which take advantage of unconventional computing to solve challenging practical problems. I care about problems in energy. This is the way that I was raised. So energy systems, and I'm in a chemical engineering department, so it sort of makes sense. But this is what we're currently doing and what I will be talking to you about in the remaining like half an hour. So anyway, before I get into the details, any questions, anything? Oh, I see stuff in the chat here. Sorry, let me so can everyone, oh, okay, yeah. Have you designed your algorithms in gate-based model besides quantum annealing? I see them now, great research. Okay, thank you, David. Yeah, I'll be talking about that in a second. Yes, I do work in gate-based modeling as well. All right, let's keep going. So let me shift gears. I'm in a physics building, in the physics department, better start talking physics, right? And let's talk about the Icing problem. So in the Icing problem, for those of you that are not very familiar with it, it's a very, let's start with some like cute physical observation made by Pierre Curie, which is if you have a magnet and you heat it up, it stops behaving like a magnet. And it is absolutely mind-blowing if you think about it for long enough. Because if anything, like one of the intrinsic properties of this material changes drastically at a given very, very specific temperature. To this day is known as critical or Curie temperature. And then you can start asking yourself, like, why? Why is this behavior changing so suddenly? Especially if we sort of consider this fact that nature likes like these low energy states. So these least energy states suddenly change radically. Why? So you can start building like a mental model about this. And let's assume that the magnet is two-dimensional, and the magnet is composed of tiny magnets, right? Indivisible magnets that can be magnetized either north or south. And they are sort of connected to each other. So you can account for the total energy of this thing and realize whether it's being minimized or not. And that's precisely what Lenz proposed in the 20s. He gave that problem to his student Icing. Icing took and solved analytically the one-dimensional case. Therefore, the model took the name of the student and not of the professor. But basically, is this energy function over here, where you're minimizing the energy, like you have things that can be -1, +1, green or red in this picture over here. And you have terms that basically describe the interaction between neighbors in a given lattice, right? Which is this term over here. And it's, so you can, depending on the sign of J, you might realize that since you're minimizing this stuff, you might have cases where it's preferable for things to be like counter-aligned or aligned, right? And then there is an extra linear term over here, which accounts for the interaction with the environment. And using this model alone, you can start explaining, for example, when you start increasing the temperature in systems, that some of these greens or -1s or something, they flip to red. And certainly here, we all agree that it's more green than red. So we can account that this is a magnetized material. And the moment that things start flipping, eventually it gets to as many reds as greens. So basically, this is not magnetic anymore. Anyway, this line of research has led to many developments in physics, including a couple Nobel Prizes here and there. And it, I would say I added this because we're in physics, right? There is this general lesson, which is the notion of universality, where systems that have the same number of dimensions and symmetries, they go through identical phase transitions. These phase transitions are these sudden changes in behavior that we can start explaining through these models, right? Because the Icing model is the simplest one in theory space that can capture this kind of behavior. Now, this is relevant to this talk because that energy, like the minimization of that energy, is a subcase of the discrete nonlinear optimization problems that I was telling you. Yeah, it's quadratic. It has no constraints in this particular case. It has binary variables because you can map those -1, +1 to 0, 1s, and you're optimizing. So people call this quadratic unconstrained binary optimization, or QUBO, and is a subcase of the problems that we're dealing with. So interesting, really interesting. So we want to solve this. And then here I usually, like, if you were paying attention to my previous slides, I told you, well, Icing solved the 1D case, Onsager solved the 2D case. Like, didn't you guys solve this already? Like, what are you talking about? Like, aren't you? And here I realized that there is like a semantic dissonance between different fields. What solving means in this building might mean something different in another building, meaning physicists versus optimizers. And in fact, for physicists, people do care about like thermodynamic expectation values, right? They look at you can say that in this picture, like there is more green than red, and here they're basically half and half. Now, what happens is that for optimizers, usually since we are looking at the variables of each variable individually, we do care whether the corner one is green or red, because sometimes it can represent whether pilot A goes to aircraft 1 or not, right? So that's something that needs to be addressed, because you sometimes, from previous experience, I give this talk to physicists and I just tell them like, oh, I'm solving Icing models. And they're like, well, just read a book, right? I mean, they're already solved. And in fact, no, they are not for the applications that we care about, because I care about each one of the variables. Okay, how do you do this? Because you can draw this kind of cartoon where you're looking for this minima, global minima, you can have local minima, and you want to basically explore this landscape. So there are Icing solvers. Okay, fine. What's an Icing solver? End-to-end solution method. And it might require, like, including software, algorithms, and hardware, or let's call them machines. And under that definition, there are a lot of tools out there to help us solve Icing models. So classical algorithms, maybe you have heard about something called simulated annealing, or that I'm calling here classical thermal annealing. And then there are these quantum annealers. There are algorithms for gate-based models that I just got a question for, that include variational quantum algorithms and so forth, QAOA and VQE, and other machines. That's something that is actually very interesting. And this might be a really promising and fertile ground while we sort out how to build large quantum computers. A stepping stone, which it's still very rich, could be, what about if we just keep designing specialized hardware to solve problems of interest? Among them, the Icing model, right? People can even argue that quantum annealers are precisely that. They're just like custom hardware to solve this particular kind of problem because of how interesting and challenging it is for classical machines. Whether they use quantum or not, sure, like we're doing quantum computing, right? We need to sort of have a programmable way of dealing with quantum mechanistic effects or phenomena. But this can still be fairly practical and fairly useful. And so I'm just dropping it out there and hopefully gathering some impressions here. So anyway, quantum computing talk. How do you do optimization using a quantum computer? So we will start with something called the quantum adiabatic algorithm. And the quantum adiabatic algorithm, basically, you design it based on the adiabatic theory. And basically, what you have, I like to be like this visualization, I find it beautiful, which is you have that landscape that I was telling you about. And this red dot defines like the solution that hopefully it's sitting on the lowest valley of this landscape. So usually, like classical algorithms, they move the red ball around this landscape, just looking for that valley, that lowest point. Now, in the quantum adiabatic algorithm, what we're proposing is the following. How about you have this landscape. Assume that it is easy to set up, easy to put the red dot in the bottom of that landscape, and then you start slowly, very, very slowly and carefully modifying the landscape into this purple one. Okay, if I can tell you that if you do it slowly enough and under adiabatic conditions, the ranking of the energy, which in this case was the lowest energy point, is going to be conserved throughout this evolution. That's super useful because if you think about it, you can this purple landscape can represent the solution of a challenging optimization problem. And the green one is easy to solve. So suddenly by doing this evolution, the way that this system is sort of temporizing, well, through quantum mechanics, so maybe that's an incomplete way of describing it, but the way that the solution is just rolling down this new landscape is solving the problem for you. It's amazing, right? I mean, nature is solving the optimization problem for you. You just need to define this adiabatic path. And you have like even convergence guarantees with this quantum adiabatic algorithm. That's cool. That's really cool, in fact. Now, obviously, this is a theoretical algorithm. It requires conditions that are unphysical, like 0 Kelvin temperatures and so forth, and trying to do this evolution adiabatically. But you can try. You can actually try really, really hard. And then you cannot go to 0 Kelvin, but you can go to 15 millikelvin or so. And this is exactly what these D-wave quantum annealers machines are doing. they try to follow this quantum adiabatic algorithm to the closest that it can be physically done. So, and then they try to perform this adiabatic evolution. And we do have access to these machines, and this is more or less how they work. So certainly, like, you're going after an impossible goal, which is going after this sort of high-level algorithm. But I mean, it's still useful, and you can design machines for this, and it's great, right? From an optimization point of view, this is a heuristic. It will not give you like guarantee, contrary to the quantum adiabatic algorithm where you do have convergence guarantees. In the second one, you just lose them because of the physical reality. And there are a bunch of physics and physics-inspired methods that also use this kind of stuff. Here, I also, since trying to predict the fact that people were more concerned about gate-based quantum computers, so here I have a recipe for you. If you are using a gate-based computer and you still want to solve optimization. So I would claim that mapping to QUBO problems are still useful because they look like some Hamiltonians in quantum mechanics that people care about, and we can implement like this nearest neighbor kind of like two local Hamiltonians even in gate-based computers. So let's stay in the QUBO word for a second. You map your optimization problem to a QUBO, to that purple landscape. You assign this mapping is also interesting because it's sort of cheap in terms of resources, in terms of qubits, because basically each qubit represents each one of the variables that you're dealing with. So that's cool, right? In a world with few qubits, you want to be sort of cheap in terms of how many you're using in your algorithm. Okay, cool. Then let's say that you apply a circuit, and you apply the circuit aiming to maximize the probability of measuring the optimal solution of that problem. Once you have that circuit, you run it, you measure it, and because of the stochasticity at the measurement step, you might have that optimal solution with some probability. So you just repeat it and you get a bunch of samples. Certainly, like step number 3 is really challenging, right? How are you going to design a circuit that maximizes the chances of measuring an optimal solution that you don't know? If you knew the solution, stop right there. What's the point of even designing a quantum algorithm for that? So, but for here, there is this proposal, which is called the quantum, actually it was originally called the quantum approximate optimization algorithm. Then it got rebranded at NASA as the quantum alternating optimization ansatz. And certainly this is a variational algorithm, right? So the way that it uses quantum computers is that you have a circuit that it has parameters, and then you use like a classical loop to update those parameters. I mean, variational algorithms are super useful for our current noisy intermediate scale quantum devices because they don't require you don't need to do that much computation on the quantum computer because you cannot do it, right? Like error is gonna kill you. So you do this parameter tuning, and the parameter tuning is basically to find some parameters which people in QAOA know them as rotation angles. But even more like high level and better way of understanding them is just for how long do you apply certain Hamiltonian evolution. So basically what you're doing is the following. There is this adiabatic pathway that brings you from this initial superposition state, which happens to be the one that is easy to set up and the one that you know the optimal solution a priori, the green landscape, and will bring you into the purple landscape. And this pathway exists. And you now want to use a gate-based computer to track that pathway. So you do like the sequential applications of Hamiltonian evolution, which basically, I mean, and you can look at some of the proofs, right? When you have infinitely many of these steps, well, you have convergence proofs for QAOA just because you resemble this adiabatic path. So the parameters that you're tuning are basically how are you approximating this pathway. Obviously, like this lives on a super high dimensional manifold, and this is just a cartoon, right? It's not like, oh, find me that curve. But just for gaining some intuition, we can have a full 1 hour lecture on QAOA. But first, For those of you working on this, you already know this. So it's good to have like a new perspective on how the algorithm works. For those that are not working on this, I'll tell you how to learn this later, right? Because I have a class on this. Anyway, is this useful? The short answer is it looks like it. It looks like it, in fact. These results are from my friends at Los Alamos Laboratories. You have on the x-axis the time that it takes to solve a problem. On the y-axis, the quality of that solution. The lower, the better, because it actually measures the error with respect to a global optimal solution. You have all those colored lines that correspond to classical methods, to classical heuristics. And that black line corresponds to a Quantumatic. And notice that both axes are in logarithmic scale. So we're talking orders of magnitude speed up for that particular problem. In fact, it is so impressive that the white dots, I don't know if you can see them, those account for communication cost. Those account for sending the problem from New Mexico to Canada, retrieving the solutions back to New Mexico. It's impressive, right? I mean, whoa. Obviously, like from the optimization community, you'll be like, oh no, you're limited by size, by connectivity. That's why I was designing that compiler to begin with. And if anything, it can give you a heuristic solution. But if this corresponds to a practical application, I couldn't care any less whether like it's limited. If that is the actual problem that I want to solve, I get to solve it a couple orders of magnitude faster. That's cool, right? From the other side, from the gate-based side, it's also interesting from a more theoretical side. So basically, this is the quantum alternating. Well, in the original one, in the original name, the first A corresponded to approximate. And it comes from the fact that it's a class of approximation algorithm. For those of you in computer science, there are algorithms that can run efficiently for hard problems. And given that we don't know if P equals NP, you need to pay some price, and the price is in some approximation ratio. You can just say, oh, this runs very fast, but I cannot guarantee that you will get the optimal solution, but I can tell you, for example, that you're 80%. I can guarantee that you're within 80% of the optimal solution. And in some cases, like this is very practical. This is very interesting, right? Because you're like, okay, sure. I mean, if this runs fast, I can afford like losing 20% of optimality just for it to run. These are very theory-like kind of results, but it was interesting when they first proposed QAOA. For a particular algorithm, they achieved the best approximation ratio among any algorithm, including classical ones. So this was absolutely shocking at the beginning. Obviously, it took like classical algorithm designers, they were like, oh, they learned from that paper, and then they designed a better classical approximation algorithm that now beats that approximation ratio. So it's an ongoing race. And then like for the very, very practical people, and this might be something that some of the other people that are working in quantum computing based on a regular basis, is like, this is not big, this is limited by noise. So like the limitations are even larger for these gate-based computers, but it's really interesting. It's really interesting. And I do claim that we should invest some time with this. Okay, cool. So where do these Icing instances come from, right? Where does that purple landscape come from? Where is this nonlinear discrete optimization I was talking about? Like I sort of spent a fraction of this talk introducing you to this topic. Am I not going to use it? Like, did I make you lose all that time? Short answer, no. So there are many papers. Some people have taken like super famous NP-complete problems and mapped them into Icing models. And some of those mappings are inefficient. So if you like classical optimization, which might not be the crowd here because this is a quantum talk, but if you like classical optimization, a super easy way of jumping into this field is taking some of these formulations, and with that training in optimization, I bet that you can improve them. Then you go test them, you get some improvement because obviously, and then boom, you gotta pay, right? If you want to write one of those papers, let me know. I have like 2 or 3 of those, so we can keep just generating. We have ideas. Now, that reformulation there's a recipe. So From the more general problem, if you had continuous variables, well, you discretize them. That's an approximation, right? From now on, it's gonna be purely reformulation, so there's gonna be an exact mapping. If you have integer variables, you turn them into binaries. You just represent them as binaries. If you have nonlinear equations on binaries, there is this whole thing called pseudo-Boolean optimization that basically tells you that you can represent them as quadratics. That's good, because once you are in quadratics, you're good with the cubos. And if you have some constraints, you move them into the objective through a penalization factor. This thing can be automatized. And in fact, it's really time-consuming to do it once by yourself. So me and my group, we wrote software packages for you that have optimization problems to just, with a single line of code, transform them into cubes. And in fact, communicate with the cubo solvers. So obviously, this reformulation is not perfect. We had to sacrifice something in terms of, in order to be general, to be like just click and run, we had to sacrifice something. But still though, like it gives you a one-stop way of using quantum devices if you're a classical optimization. Now, and here comes the climax of this talk, which is, remember that part that I told you, this is what you should learn from the seminar, that part about decomposition algorithms, breaking down big problems into tinier pieces where each one of them gets solved by the right tool. How about if we apply those same concepts, but now some of the sub pieces can be easily solved by quantum research? So we do have like a classical algorithm, but we, for example, isolate the complexity of this problem into those subproblems. This obviously is not a new idea. Some other folks have had it. So people at IBM, people at Zapata, and so forth. But we are working heavily on this. And if time allows, I will tell you a little bit more about this. I'm running out of time, so I'll just fly through this. But please feel free to ask. So the reformulator, it's cool because you can just directly use it. It's written in Julia, which is a new programming language. It's done with some collaborators down in Brazil. And it's not only the fact of reformulating optimization problems into cubos, but then connecting them with all the solvers, classical or quantum, and then doing some analysis tools. What can we map into Cubo? Short answer, much more than any other tools out there, including Qiskit, right? So we have like different kinds of constraints and we're looking directly into this. What do we connect to? We already have, this code has been designed so thoroughly that the connection to the different solvers comes basically for free. If you look, many of these connections, they have been written by us, and it's no longer than 200 lines of code, and suddenly you can use quantum annealers or Qiskit or simulated bifurcation machines or coherent Icing machines or classical and hardware accelerated things. Suddenly all those become available. So that has allowed us to be basically to have the most coverage across all the other people that are doing stuff out there. Just to highlight Qiskit, we can just directly use Qiskit and look how easy it looks. So you use this Julia mathematical programming, you use our package. If you're using QAOA, you specify it like this, and you just write the model as if you're writing usual optimization models and code solve on it, code optimize on it. That's it. We took off all the weight, all the heavy lifting about reformulating the problem into the shape that quantum computers like, that QAOA understands, and you just focus on the model, and we'll give you the results, whatever the quantum computer answers. Is this mapping efficient and everything? That was something that we were really concerned with. And we spent a lot of time doing code optimization, and basically, again, in the x-axis is the size of some problems, here for traveling salesperson problem, here for number partitioning problem. On the y-axis is how much time does it take for us to write the model, not to solve. We're not solving them yet, but just write the model, which might be non-trivial, especially if you're using other tools. If you, for example, were using the stuff that Qiskit provides for you to reformulate the problems, well, good luck, right? You will be spending like a lot of time just writing down the model. And we're, I don't know, in this case, like the axes are logarithmic and we're still like ahead of them. So it's like orders of magnitude speed up that we get. This is cool. We love this. Last 2 minutes. This is some work that I was doing with some folks at NASA and at Stanford. And we were concerned with solving problems solving constraint problems with with Icing solvers in general. In fact, like the hardness of some of these optimization problems, it arises from the constraints. So, and if you're working in anything related to quantum optimization, you know that constraints are always there lurking in the corner, looking at you and being like, yeah, you're just approximating this. So we went heads on, and in order to solve a problem of this shape, so it has a quadratic objective, it can be non-convex, so this Q matrix can be non-positive semi-definite. You have some linear equality constraints. You have some of these variables being binary. It's a very general kind of problem. It helps us model, I don't know. Originally, we were thinking about neural network verification, but it helps like scheduling models look like this, logistics models look like this, and so forth. We did a grand tour around like some beautiful theory, by the way, which is called conic programming and capacitive programming, just to be able to write an algorithm, a decomposition algorithm, which eventually outputs problems that we can solve with an Icing model. So we needed to do like, I'm not telling you that this decomposition business is like already solved. Like we needed to design this algorithm and so forth, but eventually we isolated that red box is going to be tackled by a potentially quantum, but Icing solved. The rest of the stuff, we actually did some analysis, and the rest of the stuff is polynomial. You can just run it on a classical computer and stop caring about it. I will not go into the details. I'll show you how we performed. Because this is something that I again, it might be, that's why I spend some time in the background. I like testing these computers. Like complexity is cool. Don't get me wrong. It's really useful, but I'm a more practical person. So I like implementing these things and just trying to solve. So these plots are kind of complicated. So let me just explain through. As usual, x-axis is the size of the problem, which measures like the complexity of the problem that we're solving. On the y-axis is the time that we spend solving the problem. These are some well-known combinatorial optimization problems called max clique. So you're finding a clique inside of a graph, the largest one, in fact. And people usually use these mixed integer programming techniques to solve it. And there are super efficient solvers out there to solve this kind of stuff. One of them is called Gurobi, if you care. Now, you can have Gurobi, and Gurobi is the red line over here. And you can already see like this exponential complexity kicking in. It's very sharp. The red line is very sharp because we're using those confidence intervals to represent like over 100 instances how it would behave. And since Gurobi has like convergence guarantees, like that confidence interval is sort of sharp. Okay. The blue line over here is what happens if we use 2QUBO. We just reformulate this problem into a QUBO and throw it to an Icing solver. In this case, I'm not even using quantum. I wanted to go cheap, so I'm using like some simulated annealing code and calling it a day. And you can see certainly like the blue line scales better, like it grows slower, but the confidence interval is huge because this is a heuristic method. You cannot guarantee that it's solving each one of the problems to optimality. And then here we come. I just summarized because we did like some parameter settings, but we're the green line. And the green line is cool because it has the same scaling as the heuristic, but it gives it like, it also represents like the thickness of this represents like the variability on the solution. We do have optimality guarantees. We do provide optimality guarantees, yet if we're using a heuristic. And in some cases, if you already look at the larger problems, we are beating the state of the art. This, I don't know, like it's a very dense plot, so just unpacking it takes some time. But the point is, like, this is a practical way of implementing constraints into Icing solvers, using Icing solvers. So who wants to use our method? Microsoft, we're already talking to them. 1QBit, Zapata, MTT, they reached out with this stuff. In fact, there is a review on quantum optimization that came up yesterday on the archive. For those of you working in this arena, I do heavily, like profusely recommend you to read this white paper. It's 70 pages. It's IBM and NASA and Los Alamos and all the people doing this kind of stuff. And this whole work motivated a chapter in that because they really liked it, apparently. Now, who else can use this? You. We put it on GitHub. So just go use it, try it, and see how it goes. Okay? All right. So, oh, I covered this already. That's nice. How do I learn this? I designed a class back at Carnegie Mellon with the support of the Air Force Research Lab, the Center of Advanced Process Design, the Tepper Business School, which I am affiliated with these days. And we included quantum integer programming, quantum optimization, and quantum machine learning. It's been taught, it's part of the training material of the Air Force Lab and the Feynman Quantum Academy at NASA, at USRA, sorry. AWS supports us. They tweet about us and all this stuff. And as usual, we put it on GitHub. So recordings, lecture notes, codes, slides, everything is there. I think I will, like currently there are students taking it back at Carnegie Mellon. I think I will start offering here at Purdue, maybe next year when after my teaching relief. So yeah, cool. Let me just wrap up. Sorry, I'm running out of time and there is a question. So how about if I answer the question and then I wrap it up? Oh, sorry. Yeah, my bad. So let me, I did promise some perspectives, right? So let me give you some perspectives here. Foreseeable future. So left side, classical Roman sculpture. On the right side, there is this beautiful sculpture, which is called the Quantum Man. So, and it's like, basically, if you start moving around it, it sort of disappears. And whether people, like, if that's what you care, how you understand quantum mechanics, good for you. That's great, right? It's beautiful, regardless. And I do that. So the foreseeable future, how I see things happening, is that the Quantum Man is talking, is speaking. And this is one example where IBM released this paper, this cutting through the noise, which is basically error mitigation and to like walk towards fault tolerance even with near-term quantum devices. And they had like these numbers that would back this up. Okay, cool. Well, classical man answers. And within 2 weeks, 3 different groups in the archive, including some of my coworkers at NASA, released classical algorithms based on tensor networks that would basically solve this thing on a laptop in a fraction of a second, right? So my question to you, to the audience, is who won this discussion? Who won in this thing? And the answer is us, right? As a community, the sole fact that we are looking at things differently is making, even in the classical world, advancements in algorithms. Now, suddenly we have a tensor network algorithm that is far more efficient for that particular problem than whatever we used to have before. So this is going to be an ongoing conversation, and we can replace these bubbles with the quantum supremacy claims, or with QAOA, or with the algorithms that I just showed you, right? I cannot wait for classical development to catch up with the stuff that we have been doing. So perspective, right? I'll wrap up here. That thing points to the Sequoia website, and I do thank you all for your attention, both here and virtually.